All right, wanted to talk about power and efficiency for just a moment. So we can define power as the rate of work, the rate at which work is done. So we can say how much work is done over some time period, delta t. So we just finally introduced time into this whole unit, right? We haven't looked at time yet. This would give us our average power done. We'd have to say so much work was done and it took 4 seconds to do so. So you could figure out how much power was done, maybe from a force lifting an object, any of the forces that we've looked at, right? Often more valuable would be the instantaneous power, and so if we had the work and took the time derivative, we get a instantaneous definition. So it just depends what kind of information we're given, which one we'd use. If we were given a time interval, then we would use the one on top. If we were evaluating it at some specific point, then we would use the instantaneous. Okay, let's take a look at the units. If this is work per unit time, then we have a joule per second, and we're going to call that a watt. It's not always given as a watt, and so we can say that 1 watt is equal to 1 joule per second. And they relate it to a lot of other things like foot-pounds per second, and I think rounding we get 0.738 feet-pounds per second if you were in customary units. Often you'll actually see horsepower. This is probably the most common. So be able to convert horsepower. 1 horsepower is equal to 550 foot-pounds per second, or 746 watts. So I would say this one will become more handy to solve the problems. Now, this is a rate, so if you have a watt, you can take this and multiply it by time and get what's called a kilowatt hour, or you may have seen a kilowatt hour before. And that's how your energy bill is. It's in kilowatt hours. So we can express the work by multiplying it by time. So we end up with joules again. So I put kilowatt hour just because that's what's on your energy bill, but a watt hour. All right. I have a little RC helicopter, and how much battery capacity is in there is in milliamp hours. It's kind of another weird unit, but we can relate these two. You'll see when you get into your next physics class. For now, let's just know that you can get the total work done, divide it by the time it took to do that work, and that is the power. Okay, let's take that derivative definition again, and let's derive one more thing. So we have, power, P, is equal to the time derivative of the work. Okay, well, if you remember that work was equal to some F cosine theta, let's go ahead and substitute that in there. So we'll have the time derivative of F cosine theta, and we end up with an x in there, right? And then this is a dt. So the work done is always the force times the displacement. And let's put this d with this x right there. and pull this force out. So we get F cosine theta times a dx dt. And what's that? That is the instantaneous velocity. So we have another definition for power that we can use. We can say that power is equal to the force dotted into the velocity vector, or F cosine theta times the speed. So depending on what you were given, you can use either of those definitions. There's a couple problems in, I think, homework 7 that require the last couple problems, but real basic definitions. Then last thing I wanted to talk about was efficiency. Efficiency is one of the broadest terms ever. The rate at which you paint a house has to do with how efficient you are. How much, literally, you can relate efficiency to anything. How efficient is an engine? How efficient is an engine at turning gasoline into usable energy? How efficient is a solar panel at turning photons into electrons? How efficient is my thermoelectric material that I produce at turning phonon scattering into electron flow? But it's also like a money thing too. You'll see it in economics. You'll see it in what's the efficiency if I mix these chemicals together? What's my yield? But the basic definition for efficiency, that you can always just remember this, is how much you get out over how much you put in. If you remember that, you'll be okay. You just need to relate it to whatever quantity you're talking about. So if you're talking about the efficiency of maybe a force, let's write it. So certain things like maybe if we had a lever and a fulcrum. Remember, if you have a fulcrum and a lever, it allows you to apply less force but get more back out. Well, that we can find out the efficiency, how much we get out over how much we get in. And so that would just be F out over F in. So whatever quantity you're talking about, it's just how much you're getting out over how much you put back in.